All right, so you have your handouts. I emailed it to you along with this video. Please take good notes as you watch my video, all right? So you can see in your first box it says intermediate value theorem, and usually I just call it IVT, and you can actually use these three letters on your AP exam when you want to refer to this theorem, so you can always say by the IVT and so on. So this is how it works. The first condition, you can apply this theorem only if the two conditions work. First one, your function must be continuous on a certain interval from A to B. That's number one. Number two condition, it says f of a, so these are the two endpoints, f of a and f of b. So it says there is a value k where k is greater than f of a but less than f of b, or k is greater than f of b but less than f of a. Then, in that case, they say there is at least one value of c, at least one value of c on this interval from A to B, not including the endpoints, such that f of c equals to that value of k that I just mentioned above. So let me show you how this looks on a graph. So I had to pause for a second so that I could draw a nice graph for you. So you can see we have a graph, it's continuous function, and I'm considering this interval from A to B, and I marked my endpoints in blue. And so the first condition works, the function is continuous. The second condition, it says there's a value of k. See, I marked it in red on the y-axis. And it's between f of b and f of a. But you can have f of a on the top, f of b on the bottom. And then you can always find a value of c, at least one value of c between a and b on the x-axis, of course, where the f of c equals to k. Well, that makes sense, right? I hope so. I'm just going to put here f of c is the same as this little guy, k value. Okay, we're going to try to apply these theorems to different problems. But this is our first theorem. Now let's move on to the next one. I hope this one makes a sense. Number two theorem, and it says, this one I used, what color did I use? Red. Okay. Extreme value. Extreme, sounds so dramatic. Extreme value theorem. All right. Again, the first condition, you can apply this theorem only if your function is continuous. Okay, on some kind of interval A to B. Then we say there must be an absolute maximum and absolute minimum on the interval A to B. So let me write it down. So the function is continuous. Then there must be, and I'm going to explain what the absolute maximum, minimum means. An absolute maximum and absolute minimum on this interval. And by the way, notice I included the A, and B. These absolute, we call them extrema, they can occur at x equals a, as I said. You can consider the endpoints x equals b, or it can occur at any, let's say, any critical value of your function f of x on this interval. Now let me explain something here. So let's say I have this kind of graph, and it's the function is continuous. You know what, let me just, I'm going to pause and I'm going to erase this graph and draw a different one on the new page. All right, so here's my continuous function, and I'm considering this certain interval from A to B, and please notice I actually close these two. I actually filled in these two circles. Now, because we do want to include the endpoints in this case. Now, absolute maximum, absolute minimum, or we call them absolute extrema. So, look at this point. When x is b, you see the value of x, the value of y. And let me put f of b. In this case, the y value, when x equals to b, is the largest value. Agreed? Now, that's the highest point. Now, what's the minimum value? Not x equals a, I mean f of a. It is your endpoint on the left side, and the x value is the minimum one, but we're not talking about the x value. We're talking about the y values. So what's the lowest point here? I hope you noticed this. It's right here. So the highest one is up there, and the lowest one is here. So let's mark it as, I don't know, let's say it's C. So it's f of C. And on the top you have f of b. So this point, when x equals to b, we call it absolute maximum. Well, the absolute maximum occurred in this case on this interval at this endpoint when x equals to b. Now, the absolute minimum, I call it f of c here. Well, I don't have any certain values, but in this case occurs when x equals to c, and that's your lowest point. Okay. Now the IVT, one more time, says if your function is continuous, then you must have an absolute maximum or absolute minimum on your interval, and you can obviously consider the endpoints. Now you're probably thinking, okay, so this one looks like a polynomial function. What about if I had something like I don't know, logarithmic kind of function? So in that case, what happens? Okay, so fine, same thing. Let's say I have my a value endpoint here, and my b value, the endpoint is there. So you can see your function is continuous on this interval. Now the highest point, the highest value, would be f of b. And your lowest value, lowest number here, look at this, it's f of a. So even though I don't have any, critical extreme in this case, but still, I have an absolute maximum and absolute minimum, right? And my function is continuous. So that means in this case, I can actually, apply my extreme value theorem. Now, let's move on. Number 3, the box number 3. And this is Rolle's theorem. We don't put RT. Normally we actually say the whole expression. So we say Rolle's theorem. I like this theorem. It's so helpful, and it really makes sense. Again, f of x, the first condition, it has to be continuous on, and notice I included the endpoints. Second condition, f of x has to be differentiable. That's very important. Did you notice I didn't mention that previously, but in this case it has to be also differentiable on not including the endpoints, because your function cannot be, it's not differentiable at the endpoint. Okay, so, and one more condition. If, okay, so you take one endpoint and you say f of a, take the second point, find the y value, and you say f of b. If they're exactly the same, the value of f of a equals to f of b, then we say there is guaranteed a value of c. So there is a value, some kind of value of c on, not including the endpoints, on your interval from a, between a and b, such that f prime of c equals to 0. Well, it is actually very simple. Look at this. I don't need to use a different page. So let's say I have this kind of graph, something like this. Let me actually extend it. Polynomial. Now I want to consider a certain interval. So let's say this is my x value a, and this is my x value b. Now please notice, well, this graph is not perfect, but please notice that f of a in this case is the same as f of b, right? The y values are the same. Now, according to this theorem, we say if the function is continuous, we have that, and it is differentiable, we have that, and f of a equals to f of b, and we have that, then we're supposed to have some kind of value of c between a and b, where the derivative of that equals to 0. When does that happen? That happens when your derivative equals to 0 at a certain x value, when you get the maximum or minimum point, right? When your relative maximum occurs, then the tangent line, the slope of the tangent line equals to 0. When you get the relative maximum, the tangent line, of course, the slope of that line equals to 0. So in this case, I'm sure you can see where that guy is, that little c. It's right here. So if I draw a tangent line that touches my graph at this point, so what's the slope of this tangent line? It's 0, right? So then f prime of c means f prime of c equals to 0. So let me just write it down. So it is so simple, and I don't think you really need that much explanation here, and I'm sure this makes perfect sense. But if you don't understand, please pause and WhatsApp me immediately. So I guess we can move on. All right. Next theorem. It says mean value theorem, and we call it, we're allowed to use MVT. The 3 letters, mean value theorem. Now, the first condition, your function has to be continuous. Oh my God, what else is new? Continuous. On this interval, including a and b. Your function f of x must be differentiable. On, obviously we're not including a and b. Then we say there is some kind of value of c on this interval. So there is a value of c on, don't include the endpoints, on this interval, such that, all right, f prime of c So the derivative of your function at this value of c is the same as, what does this remind you of? Do you recognize this expression? This one right here? I'm sure you said probably, or you had this thought. Oh, it's the slope. Slope of the secant line, right? So let's see how this works graphically. I'm going to use this same page. So let's say I have my function f of x, and it is continuous. So looks something like this. And I have the two x values, a and b. So let's say one is here, and that's my a, and b is up there, x equals b is here. Now, it's continuous, it is obviously differentiable on this interval, and then we say there is some kind of value of c, so between a and b. You know what, I'm gonna, it's not easy. Okay, so let's say it's somewhere here. Okay, that's your value of c. Now, the derivative of this function at c, what does it mean? It means the slope of the tangent line at this point, right? At x equals c. So, you know what, before I continue, let me draw this line. The tangent line that touches my function at this point. But now it says this derivative your function at x equals c, or in other words, the slope of this particular tangent line, is equivalent to this slope right here. How do you find it? The value of this expression. So it's f of a minus f of b. Remember y2 minus y1 over x2 minus x1. So we're basically considering these two endpoints. So the slope of this line, by the way, we call it secant line. And let me draw that line. So you can find the slope of this line, secant line, by using the endpoints on your graph, and then you can say that the value of this slope is equivalent to the value of the derivative of my function at this point x equals c. By the way, these two equal to each other when your lines are parallel, right? So you can always find somewhere between a and b a point x equals c where your tangent is now parallel to the secant line. So I hope this makes sense. And now let's practice. So next page, do you see that table? I'm just gonna pause for a second because I do want to copy this table. All right, so I'm done. And here's my table. You have it in front of you. You don't have to copy it. Let's see what they give us here. So it says the rate at which water flows out of a pipe. And by the way, I underlined, when I read this problem, I underlined gallons per hour. That's important, units. And what does it mean, gallons per hour? What kind of parameter is this? The rate, correct? So it's given by a differentiable function r of t. And the table, this table shows us the rate. So we have rate versus time. And it says every 3 hours for a 24-hour period. Part A, it says estimate the value of r prime of 5. So we need to find the rate in gallons per hour when time t equals to 5 hours. Okay, and then they want us to indicate correct units and then explain what that means. Okay, so now we all know, since we don't have a function, so we can't really find a derivative and then plug in the value of 5. We only have this table. Then we know, in order to find the derivative, we can just simply find the slope of the secant line. Now, in this case, by the way, I don't want to use equal sign, so it's approximately. So t equals 5. Where is it? 5. I don't have it. But t equals 5 is somewhere between these two values, 3 and 6, correct? So we can use those endpoints to find the derivative of this function at 5. Okay, so we're going to do y2 minus y1. So I'm going to do 10.8 minus 10.4 over 6 minus 3, and calculator, and I get 0.133. Now, units, gallons per hour, but not hour squared. How come? Well, because R of t is, well, what's R of t? It's the rate, but the units are gallons per hour, but you're looking for the rate of this rate. So the derivative of the derivative, so that's why we get gallons per hour squared now. Now you want to say since, because they want us to explain more, you say R prime of 5 is greater than 0. It is, right? Because we got 0.133. Then the rate at which, what is it, water? Yeah. Water is, it's like English, you know, and they want you to write it out, and they don't want you to make the grammatical mistakes. So you need to be careful and write nicely, and I'm sure you're good writers. Flowing out of the pipe, right, is, now since the derivative is greater than 0, then we know that this rate is increasing, right? We know when the derivative is positive, increasing, then the function is increasing, and the function in this case is R of t, increasing at t equals 5. No, I don't want to use hours. T equals 5. That's enough. Okay. Part B. You can always pause, and if you want to digest it or take additional notes, and then continue. It says, using correct units of measure, find the average rate of change of R of t from, now it says t equals 3 and t equals 18. Now, average rate of change, the slope, right? I hope that's the only thing that comes to your mind right now. So we're going to say average, and they want you to write that. It's very important. Rate of change, just write it out, equals, now show your work. How do we find the slope? Now we're considering the x values, well, t values, the endpoints, 3 and 18. Now I'm going to go back and see my table. 3 is right here. 18 is right there. So the y2 minus y1. Oh, but you know what? I need to write it. First I need to express it in this form. R of 18. And if you don't do that, you're going to lose a point, or maybe half, but still, it matters, right? So please show your work. 18 minus 3. And then you're just going to, you have your table in front of you, right? And I have it on the computer in front of me, so I'm going to just, I don't want to jump from one page to another. So R of 18, 10.7. R of 3, 10.4 over 3 t minus 3. And the result is, you can verify with your calculator, 0.02. Now units. We found the rate of change, and the function is of R of 3, of R of t, and R of t is the rate, so you're looking for a rate of rate, so that means we're using the same units, gallons per hour squared. Part C. It says, is there some time t between 0 and 24 hours? where r of t equals to 0. And this is justify your answer. Well, we're going to talk about one of these the theorems. Remember, one of them said something like f prime of c equals to 0. You can actually pause and find that theorem. But pretty soon you'll be able to tell right away that in this case, we're going to apply the Rolle's theorem. So this is how you need to say it. So you need to say since r of t is, well, it's continuous and differentiable. Well, if it's differentiable, of course it's continuous. So it's differentiable on this interval, include the endpoints. And you want to say the second condition, we're talking about these two values of t. So you say r of 0 equals to r of 24 and equals to 9.6. How come? Where did I get it from? Oh, well, look at this table. What's r of 0? R of 0 is 9.6. What's r of 24? It's also 9.6. So, and that's right here. So then you say, therefore, by the Rolle's theorem, you say there is value of t on this interval such that, I don't have enough space here, but put such that, or when r prime of t equals to 0. And that's your Rolle's theorem. And we just applied one of those theorems. That's awesome. All right, now let's move on. Next page. It says the total order and transportation cost C of x, so okay, we're talking about this function C of x, measured, okay, I'm going to underline, in dollars, that's your amount, right, of bottles of Pepsi Cola is approximated by the function. So they give us this function C of x, and it says 10,000 1 over x plus x over x plus 3. Okay. Where x is the order, size, and number of bottles, that's your x, in hundreds. And answer the following questions. Okay. Question A. Is there guaranteed a value of r on this interval from 0 to 3? They're including the endpoints, such that the average rate of change, I'm actually underlining this expression, average rate of change, because I actually want to get my own attention here. Average rate of change of cost is equal to C prime of R, and give a reason for your answer. So one more time. They're asking us if there is such value of r on this interval where such that the average rate of change is equal to C prime of r. C prime of r. An average rate of change would be the slope of the secant line, right? But what endpoints are we considering? 0 and 3. So what function are we talking about? C of x. So I'm just going to write it out. C of 3 minus C of 0 over 3 minus 0. So they're basically telling us, asking us, is this possible? Do you think this works? Well, you want to say, first of all, since C of x, by the way, you notice that it's the function is undefined at x equals 0 and x equals negative 3. But we're not talking about x equals negative 3 because this is our interval 0 to 3. So very important fact. So you say since C of x is undefined at x equals 0, then C of x is not continuous on this interval from 0 to 3, because 0 cannot be included. Now, but the given interval is this right here, so they did include the x equals 0, but the function is not continuous. Now you say, therefore, you say the MVT theorem does not guarantee value of R on this interval such that C prime of R equals C. So it's not possible. And one more time, how come it's not possible? Average rate of change, you use that to find C prime of R when you want to apply the mean value theorem. But we cannot apply this mean value theorem because on this interval the function is not completely continuous. Because if you look at your main equation of C of x, you notice that the function is not continuous at x equals -3. Well, that's out of range. Or x equals to 0. So we cannot apply this theorem.